All right. So the last lecture we looked at the voltage doubler. In this case, you've got an AC source, say of 10,000 volts. You've got a capacitor and a diode arranged like that. You can see at the point at the top of the diode or across the diode is the yellow voltage waveform. Right, it's almost like an offset AC waveform, and that's because it's the sum of the source voltage and the capacitance voltage. That voltage cannot discharge because of that diode. We then rectify that offset AC waveform and we get a DC waveform. Which is twice the peak of the input AC waveform. Again, if we close it, we can see that we get a current that flows through a load. That current causes a ripple. You can see there's your ripple there. Right. So it charges up on the rising waveform, discharges when the waveform's going down. Right, what we're going to look at today is a clever way of extending that. So that system was a voltage doubler. It's all great and everything, but components have set ratings. Not all components have the voltage ratings required to build up a high voltage device. So again, we start with our AC source. We've got a capacitance here and a diode here. So at the moment, it's the same as that offset waveform. So I'm just going to look at the voltages here. Just going to pause my simulation. So the yellow is the input waveform, the blue is the offset AC waveform, and the green is the DC across the capacitor at the end. So we've offset our waveform and then we've rectified it again. So I assume you're all happy with that. We've doubled the peak voltage. Right. So let's first of all have a look at this. So let's arrange another capacitor on top of that diode and connect it with another diode. So effectively the same thing should happen that happens to this capacitor here. It should get charged and not discharge. So let's have a look at what happens. I'm just going to connect this here so I can measure. Right, so what can you see there? Effectively, we've charged up this capacitor to be the same voltage as this capacitor. And we can measure that. You can see that the voltage across that capacitor is the same voltage across this capacitor. So look at the purple and the green, it's the same voltage. It can't discharge anywhere because of the arrangement of the diodes. So again, if we take Kirchhoff's voltage law and start looking at it, you've got your AC, you've got your DC, you've got your DC. Right, so at the top of that is an offset AC waveform. You can all see that? A thumbs up would be good. Cool. That offset AC waveform is again not really useful for us for testing. We actually need to make it a DC that we can use. Again, if we look at the capacitors, they've got nowhere to discharge, so they're all staying charged. If you look at the VD now, the red voltage, you can see that we've got a nice DC waveform. Got a nice DC voltage. That voltage is 40 kV. It's doubled from 20 kV. Right, so we've not only doubled the input voltage, the peak of the input voltage, but now we've multiplied it by 4. So we've doubled it again. If we add yet another stage, what can you see? You've tripled the voltage. Right, I'm going to take these voltage measurements off. Let's leave this one on. If you look at the voltage across the capacitor and the voltage across the diode, so from that point at the bottom of the diode to the top of the diode, whoops, it's not going to work now. Again, you need to be careful of your ratings of your components if you look at the voltage differences. Right. So let's look at connecting a load to this and see what happens. Let's look at the load first. Right, so you again can see your input waveform, and let's just move that. And you can see maybe your first stage, let's put that in. You can see this green waveform at the output of the generator. It's not quite like what we saw before. It's not quite like what we saw at the voltage doubler. If we look at that ripple, you can see it's quite smooth. It charges on the peak, going up to the peak of the waveform, and then falls as the waveform goes negative. Here it's got a bit of a different shape. Right, so again, it's charging as it goes to the peak of the waveform. It's discharging as it goes down, and then there's a sudden little drop there just before the negative peak of the waveform. Right, that's due to the switching of the diodes. Right. I've just plotted the voltages across the diodes. I'm just going to get rid of the main voltage. Right, so we've got purple at the top, red in the middle, and blue at the bottom. Would you all agree that the greatest contributor to the ripple is the bottom capacitor? Thumbs up would do, or not. Thumbs down if you don't agree. Right, what you can see with the purple diode is there's not much ripple. Sorry, the purple capacitor. The red capacitor, there's a little bit more of a ripple, and in the blue capacitor, there's quite a lot of the ripple. So maybe we can explore that a little bit and understand it. Right, so to try and understand it, we're going to have a look at the currents coming from these capacitors here and going through the load when it catches up. Right. So the current through the load, it looks like a DC, doesn't it? I'm just going to get rid of these quickly. Right. It's not the best, but the current going through the load, it's just a DC current. So that current is drawn from the capacitors in this column. But let's think about it. If this capacitor transfers a current or a charge to the load, it needs to be recharged by this capacitor. And there you can see it. This capacitor in the green would need to recharge the purple capacitor, which needs to recharge the blue capacitor, which means it needs to transfer one charge to the load and one charge to the purple capacitor. Let's look at the next one. Once this green capacitor is discharged, it needs to be recharged by the other green capacitor, which needs to charge that. That in turn needs to be recharged by the yellow capacitor. So this capacitor at the bottom, the yellow, is responsible for recharging the green purple capacitors on this side of the generator. These are responsible for recharging those, and then the charge gets delivered to the load. So the most charge is coming from this bottom capacitor. Right, it's not overly clear with the currents. Let me just take a few off again. But you can clearly see that the blue capacitor has a lower current than the green capacitor, which has a lower current than the yellow capacitor. All right, let's look at some better definitions of this. So we've got our circuit diagram there. We've got our capacitor. We're going to name it stage N at the bottom. And we're going to call each of the nodes N-1, N-2, all the way up to N dashed at the top. We're going to refer to this column as the oscillating column. Remember, this is the column where you offset the AC waveforms. Right, if we look at the other side, we're going to call this node at the bottom N, and then as we go up towards 1 at the top. We're going to call this column the smoothing column. You saw in the simulation there that it smooths the offset AC waveforms to like a nice smooth DC. Right, if we look at our waveforms, our blue over here is your AC waveform. I've drawn our VCN as your DC in your capacitor. Your first red waveform, Vn dashed, is the voltage Vn dashed at that node. Vn is the voltage across that capacitor, capacitor Cn. Right, so we get 2 Vmax from our first stage. So we've doubled the voltage. When we added another stage, we offset the AC waveform even further. Right, and we rectified it to get 2 Vmax, so 4 Vmax. You must notice here that the AC is now offset by 2 Vmax, not like the first stage where it was just offset by Vmax. And we can continue doing this until we get 2N Vmax. This is when there's no load connected. You'll notice that the DC in the yellow is a perfect DC. Right, so we've looked at the no load case. Let's look at the ideal case with perfect capacitors and perfect diodes and the charge just flowing. We've seen a similar equation before. Q is equal to IT is equal to I over F. So let me just get the simulation up again. Just going to pause it there. Let's put the AC waveform in. Right, so in this case, we've got a 3-stage generator. For our ideal case, it would be 3 times N Vmax. So if our Vmax is 10 kV, we would have 60 kV perfect waveform at the top there. What you can see when there's a load connected is that there's not only a ripple, but it's not reaching the 60 kV. That's because it's discharging into that resistance and that's causing a voltage drop. It can never recharge fully. Right, so when there's a load connected, there is a voltage drop, delta V, and there's a ripple. In ideal case, your charge would just be related to your total capacitance, and your ripple would be given by that. But what's actually happening in this device is that C1 transfers Q to the load, C2 transfers 2Q, 1Q to the load, and 1Q to C1, or C1 dashed. Remember here, that's C1 now, that's C2. So C1 transfers 1Q, C2 transfers 2Q, 1 to here, and 1 to the load. Etc. down to Cn, which transfers 1Q to the load and n minus 1Q to Cn minus 1 dashed. Effectively, the bottom capacitors contribute most to the ripple. Assuming that all the capacitors are equal, we can come up with an equation for the ripple. It's IT over 2 into n plus 1 divided by 2c. We can also come up with an equation for delta V naught. I'm not expecting you to derive this equation here. I would give that to you and ask you to calculate something around it in a test. The most dominant component here is the n cubed component. Remember that if it's a 3-stage, 3 cubed is much bigger than 3, or 3 squared. So ultimately, the equation can be reduced to IT over C into 2n cubed divided by 3. And at the bottom here, this sketch is important to know. You can see the voltage drop, delta V naught, as well as the ripple. You can use this equation to define the ripple as well as the voltage drop. Right, are there any immediate questions about the Cockcroft-Walton? You'll probably need to review some of the stuff that I've said. Go through the video again and look out for these page notes. You can read it in Kuffel. It's quite difficult to understand in there, but that book is available for you. All right, I think if there are any questions, maybe email me and then I'll post it onto Moodle like I did with the practical. I don't want to do all of AC today. I want to maybe just look at a couple of things and point out some practical issues that seem to be missing a little bit. You can all see the PDF that I've got up, AC test sets. A thumbs up would do. Okay. All right. Right. I want to draw your attention to, let's start with the first set of data. Your voltage at your output is 25 kV, your power is 20 kVA, your current is 800 milliamps. Let's go look at a higher voltage, 50 kV, 20 kVA, 400 milliamps. All right, I'm assuming that I power is your input power. You can see it's quite similar to your output power. You'll notice also that your power here is in kVA, not kilowatts. Remember that a lot of the time we are testing capacitive type of elements for AC testing. So you need to be referring to kVA, not kilowatts. Kilowatts is energy that we just burn. It's not the testing that we do here. So for interest's sake, let's have a look at the transformer down here. There's the PK2520. That's this one over here. Gives some dimensions, and it gives a weight of 520 kilograms. So just for 20 kVA, we're looking at half a ton. Right, if we look at the PK5020, that's the transformer with these ratings, also 530 kilograms. If we look at maybe 2580 or 2560, you can see that your size of your transformer, your testing transformer, is 930 kilograms. So that's quite large. You can see also that most of these powers are not even close to the megawatt range. Again, these are this is not equipment that's used for transmission. This is equipment that's used for testing. Right, so I'm just doing a simple example here of just a source. Of 230 volts, 50 hertz, and I'm stepping that up by 10 times. I think 10 times, yeah, 10 times to get an output voltage. Right, so I've got what is now an RMS of 210, and I'm stepping it up by 10 times, so I'm getting 2 kV out the other side. In this case, I've only got a capacitance there, right? So if there's a capacitance here, what's the power here? Right, we can actually plot that. Right, you can see it's almost non-existent. Power is in the milli. But we're still drawing a current. Let's stop it there. We're still drawing a current. The real power is almost zero, but there's still reactive power. So when we refer to high voltage equipment or testing equipment, we need to consider the apparent power, not just the real power. And that's what gives it that power rating. So I'm going to go through the practical on Friday, but I'm going to ask you all to just review real power, apparent power, and reactive power. And maybe just re-look at that series resonance circuit before the lecture, and then we can look at it in more depth. One thing that was lacking is there's a misunderstanding between